Our next speaker is Tim Peterson. He is a professor of geology at Carleton University in Ottawa.
Patterson and Carleton.
What did I say?
Peterson and Carleton.
Wow, I'm not a very good moderator. Patterson is his name. We will stay there. Patterson is his name, not Peterson. And let's see if I can get this next one right. And a senior visiting fellow at the School of Geography, that's not geology, geography at Queen's University in Belfast. Patterson's research emphasizes the dynamics of climate and sea level change throughout the past few thousand years. Please welcome Tim.
Okay, thanks very much. It's a pleasure to be here this afternoon. I'm going to tell you a little bit about some of the research that my group has been doing. So this is a very specific research project I'm going to tell you about this afternoon off of west coast of British Columbia. And I'd just like to recognize several authors here of various papers that have come out of this so far, including Andreas Prokop, who's sitting in the audience here this afternoon. And how do I get there? Just push the button?
I hope it's that one.
That one right there? Okay.
The one that says L.
Okay.
No?
Oh, there we go. Okay. So, and I presume this button makes the, what's that,
Yeah,
light?
the one in the middle
The one in the middle does the
light.
Ah, there we are, right there. Okay, so I also would like to recognize funding for this research came from the Strategic Project Grant from the Natural Sciences and Engineering Research Council of Canada, as well as the Canadian Foundation for Climate and Atmospheric Sciences. Basically, what this research involved was examination of quite a large number of cores that were taken from various inlets on the west coast of Vancouver Island and further up the mainland coast of British Columbia that were in two different oceanographic regimes. One is from something called the coastal upwelling domain, which exists all the way from the mid part of Vancouver Island all the way down to California, and the coastal transitional domain, which goes all the way from the central coast on up to Alaska, the very different oceanographic environments. So here's just some nice pictures for you to get an idea what the place looks like. It's a very nice area to do some research. This is the Tully, with a vessel that we went on into the inlet. As with all these fjord-like environments along the west coast, they're very narrow, they're very deep water, and because they're open to the open ocean around here, they get an open ocean signal, which is coming in. So you can archive within the sedimentary record in there is a very, very complete record of what you're going to find in the fossil record. Very attractive to earth scientists such as myself is the water structure in here. They're characterized, this is opening out to the open ocean over here. They have these basins that are found in here. They're underlain by very fine laminated sediments. But what's important here is they have these sills. There's a sill right here and another one here. What that does is blocks circulation from the open ocean. So out here, below this level right here, it tends to be the water becomes very stagnant, and in the inner basin in particular, it becomes anoxic. And this is very attractive for archiving very long climate records because there's no oxygen, there's no benthic organisms, and as such, there's nothing disturbing the record. In fact, the record that we find in here is probably one of the best non-ice records you're going to find anywhere for the Holocene. So very, very good. And we do this is called a CTD, conductivity, temperature, depth rosette, and we would lower this down to give ideas about water property. And further up the coast, we had to go in, this is the inlets up here, we had to use a different sort of vessel, a Coast Guard vessel in this case, because it's a very narrow entrance into this particular inlet complex, was called the Belize-Seymour Inlet Complex, and it's very narrow, but it's, once you get in there, it looks pretty much the same as we saw farther to the south. There's narrow inlets, it's very deep water, and these are images right here, some of the cores that we would take, and we'd also move to also collect records using less fancier vessels right here and some of the lakes that are found along the sides of these things. Now, so that's how where we were going and collecting our cores. Now, as we've heard in several talks, if you run up and downstairs today between this and the climatology unit, I think there's several talks here that probably should have been more grouped together here than they were. But a lot of the climate in this particular part of the world is controlled by the Aleutian Low and the North Pacific High. The The Aleutian Low, how it influences climate, basically it's a counterclockwise gyre, and what it results in is this, it influences the region primarily in the winter, it develops seasonally, and it results in, along the coastal regions, downwelling. And that's, so you end up, you imagine, in these inlets, they're narrow, it's rainy, in the winter times here you're eroding a lot of material in, and so you're going to collect material on the bottom of the inlet that's sediment, basically, and it's not very nice for organisms, phytoplankton, that like upwelling conditions with the nutrients in it, because it's downwelling. In the summertime, the North Pacific High begins to develop. It's a clockwise gyre in this region. It promotes a lot of upwelling. It's sunnier, drier sorts of conditions, and promotes, and the upwelling brings up the nutrients which various organisms are going to like. Now, what the other big influence in this region is the jet stream, of course. And if anybody, I live up here in Ottawa, or in this region right here in eastern Ontario, we watch this like a hawk, particularly in the winter time, because depending on where the jet stream is riding, north or south or whatever, it has an enormous influence over the weather. The same thing here on the west. This jet stream is going to have a strong influence over the movements of the North Pacific High and the Aleutian Low, sort of wiggles it around. And so we're going to be coming back to that again in a few minutes. Now this is just an image right here of what the sorts of things we get, the sorts of cores that we'd use. This is a piston core right here. It's dropped over the side. It has a little device right here. As it gets down near the bottom, there's a trigger, lets the core go, and you'll get about 16 meters of core. So in this area, that's about 5,000 years or so of very continuous record. The surface of these inlets is very soupy, so we have to use something called a freeze core. And a freeze core, here's some fellows filling it up right here with dry ice, and it is lowered down to the bottom where it's very soupy. It sits there for about 20 minutes. And then you bring it up with a beautiful record frozen to the surface of it, so you can capture that sediment-water interface. So you can get the now, basically, in this record. And here's what the records look like right here. So here's what the mud will look like that you bring up, sort of nondescript. But if you start to X-ray it, this is what you're seeing, okay? So you're alternating between dark layers and light layers, and this is a very excellent record. I can't underline this enough, how good this record is, because you're looking at seasonal record here of basically dark layers laid down in the wintertime when the Aleutian Low is dominating and it's raining, and the light layers are the diatoms, the phytoplankton, for example, when it's North Pacific High dominated, and you have upwelling. And that's really important. And I think if you look at this, you'll see something interesting as well, is that no 2 years are alike, okay? Basically, you should go through this record. This lends itself particularly well to looking at the various diatoms and so on in here, but also doing something called time series analysis. And so we go in and X-ray it, and we start to scan these, the cores in here, and looking for patterns that we can go. And because the record is so good, it allows us to recognize very long-term patterns that have existed for a very, very long time. And here's just one example right here. This is a freeze core taken in the inner part of the inlet, and you can look at this record going year by year by year. You can count the varves in it. This one, there was an earthquake in here, so you could see what the bottom was. It topped out in 1993 in this particular one, but you can see that some years are thicker and some are thinner, and you can look at the diatoms and so on as you move through this. So there's lots of ways that we can see what's happening. Now, why this started to become interesting to us, the main reason I got this whole money in the first place, and it was quite a lot of money actually, was on the West Coast. People have not lived there all that long, at least Europeans with things that we would do. And there are major fisheries in this area, and they had a problem that fisheries would periodically collapse. And I'm not talking about salmon fisheries, I'm talking about commercial species like anchovies and herring and so on, but their records only went back into the mid part of the 20th century. So they wanted to see what was going on with the long-term record in this region. So this is why we were supposed to go back and look at, can we see cycles and trends in the record, and be able to use that for commercial purposes to try and promote or to tell what might be happening in the future. Now the interesting thing is we started to do this analysis. We did various sorts of time series analysis. Here the first thing that we did would be a simple power spectra. And a power spectra over here, basically just looking for a pattern that tells you that there's some kind of signal in here. And what started to pop out, we began to see 11-year cycles. And that was kind of interesting as this is through this freeze core we were looking at. Then we said, well, let's do a wavelet type analysis. So this was basically just looking on the counts of diatoms that are going on here. Now we did a wavelet analysis looking at the sedimentary core. So what you do here, and I'll explain what a wavelet is just in a second, it looks very psychedelic here. Basically here is this freeze core, and the computer goes in and scans the X-rays and looks at the variation in grayscale values as you go along through this year by year by year by year. And when you do a wavelet analysis, it can go in and look for patterns at many different scales. Okay, it can look at annual level patterns in here. It can also look at longer level patterns in here. So you can see them all simultaneously. And so what we're seeing here with the wavelet is this is the annual record right here, kind of splotching across here. But you're looking at this whole core. So this is the visual. This is what the computer is interpreting as a record. But the interesting thing start to pop out is we saw this sort of a 10 to 12 year cycle throughout this entire record, starting to pop out as these, again, like sunspot cycles. Also of interest, in the early part of the record, there was a 2 to 5.6 year record in there, or 2 to 6 year record that seemed to be something like an El Nino that terminated strong El Ninos that terminated around 1976, which, if you know anything about the Northeast Pacific, that's the major regime shift that occurred up in that region. So we also had a pattern change, and I saw a talk earlier today by George Taylor, and he saw something similar going on with some of their records. We also saw that these very interesting patterns start to emerge when we looked at the longer core. So this is a whole core going back to about 4,700 years. This one tops out about 1,800 years right here. And again, this is a wavelet. The wavelet at the top of it here is looking at patterns at short time. So imagine if you had the whole core laid out here and looking at all the grayscale value changes. So we could see these shorter patterns and longer patterns down here. So the interesting thing was, and we start to see lots of things that look like sunspot cycles at various sorts of scales in here. There was the 11-year sunspot cycle appeared, but of most interest that I'll talk about right here is we start to see the 75 to 90-year signal in here that began to pop in and pop out, pop in and pop out, and we began to see other cycles that sort of would change. This marked a major a change in this region. It was called the Tiedemann neoglaciation in this region in the late part of the Holocene, and we saw this sort of a change in stationarity as we moved in the cycle. But the big interesting thing is looking at these Gleisberg cycles right here, these which are solar cycles. They'd last for a while, they'd fade out, they'd come in, they'd fade out through the entire record, and that was kind of interesting. So at this point, we were sitting, we should be seeing these things, okay? Because there's problems with sunspot cycles. And for what we were getting the money for in here, we also began to see lots of interesting cycles showed up with the fish that we were looking at. And the way we could look at fish as proxies in here was to look at their fish scales. Okay, so this is what we just basically quantify them. You count the scales of different species, and we'd have to occasionally do sorts of corrections in case we cored a whole fish or something, and you'd have to correct for that as well. But the same things start to pop in. They would see these cycles, they're roughly in the Gleisberg cycle, sort of fading in and fading out frequently for long periods of time. And this is why we were getting the money here, basically, because there'd be one fishery would seem to last for centuries, and then it would just go away. And like really quickly, it would disappear and then it would come back again. So we start to wonder, why might that be happening? And why are we seeing all these things that look like sunspot cycles in here? Now, interesting, and so I started to look at the literature, and I hadn't really explored all the sunspot literature, so I'm just kind of, in particularly for this crowd, these slides are unnecessary since we've seen them 800 times today in various talks that you've gone through, but everybody realizes that you go through various sorts of sunspot cycles. We're just finishing off sunspot cycle 23, and we may or may not, but depending on what talk you go to here, be starting into sunspot cycle 24 here, and the way it works is there's, at the trough of the sunspot cycle, there's no sunspots, and everybody's busy watching for the next sunspots right now all the time. And as you move towards a peak of a sunspot cycle, they begin to move from the polar areas or right here down towards the equator, and this is what you'd get at the peak of a sunspot cycle with lots of flaring, and that provides lots of energy out into the solar system, which bombards our planet. And we've also seen this slide innumerable times today as well, or some variant of it, which shows us that there's a variation in the total solar radiance across an 11-year sunspot cycle, which amounts up to about 0.1% or 1.4 watts per square meter, which in the big scheme of things is not that much, okay? And this was why I was having some problems early on when we were starting to look at our data, is because if you look at the literature that was in existence at the time we were starting to develop these ideas, there's just not enough energy across the sunspot cycle to drive the sorts of changes we were seeing in the sedimentation rate and in also with the diatoms and the fish and all the other sorts of things that we're seeing, although lots of other studies had come out and shown similar sorts of things, hundreds of them literally. So what was the explanation? Well, luckily for us, all these papers start to talk about amplifiers. One of my major influences was Jan Weiser at the University of Ottawa. You may have heard of him, has done major studies of this sort in deep time, but also the work of Svensmark and various other sorts of people. And looking at clouds, and I'll just spend a moment on that in case somebody somehow missed one of the talks today. I've already talked about this. So clouds basically can act as a climate change amplifier, and this is just basically you can have either heating by clouds or cooling by clouds, and depending what sort of clouds that you have. If you have a low-level stratocumulus cloud, that's ending up going to cool something. If you have a high thin cirrus clouds, it'll allow light to pass through, which will block thermal radiation, result in some warming. But overall, the more clouds you get, you end up with a cooling effect overall. The other part of this puzzle, as we've all seen today as well in different places, is cosmic ray flux. And everybody realizes that cosmic rays are these high-energy particles. They're made up of bits and pieces of neutrons and protons and all sorts of things that are continually bombarding our solar system. Here's us in the Milky Way right here, and here's basically the various supernovae that occurred through the last 100 years. So we've been whacked by these things continually. In fact, there's about 1 supernova per second somewhere in the universe. And if you look in deep time, this is you can see as we move in and out of these the solar arms, and here there's been suggestions as to that may explain why we move into major glaciations and interglacials, which is not this story today, but that's an interesting story all in itself. So here's the cosmic rays are continually bombarding the solar system, and counteracting that is the solar wind. And that solar wind is being influenced as it moves through a sunspot cycle. So if it moved to a peak of a sunspot cycle, a little bit more solar wind, and if a trough, there's going to be less. And then we're moving on to into the Svensmark range right here. We found this interesting correlation between sunspot cycles and galactic cosmic rays and global cloudiness. And it shows a nice correlation here, and here's another one shows the same sorts of relationship. And the interesting thing is it's about a 1.7% variation, this cloud cover, as you move between a solar maximum minimum. And I found it really interesting, start to read it, that actually about 1.3 watts per square meters, which if you add that on to the 1.4 watts per square meter is an amplification. Okay, so you end up with about 85% of what the projection is for what global warming from CO2 would be across since the beginning of the Industrial Revolution. So that's big stuff now. So also of interest to me, and here's basically the model, okay? So basically here's a sunspot cycle right here, and continually the sun is flaring, which will influence us. As we move into a peak of a sunspot cycle, you get satellites taken out, or it'll knock out the Quebec power grid, or all sorts of things that will happen periodically here. But that has an influence over the galactic cosmic rays. So during a peak of a sunspot cycle, more of these are being diverted from the solar system, basically, and away from the Earth. And during a trough, you'll have few of them, and more cosmic rays will get in, and we end up with this pattern in the cloudiness and the 1.7% variation and so on, and that has an impact. That's all very interesting. And here it is, but what interests me as well, looking in deeper time and looking at some of the longer cycles, though, is that as you start to move up into the Gleisberg cycles and Seuss cycles and so on, there's an amplification of that effect as well. And in fact, it works out that it'll increase the intensity by a factor of about 3 to 4, which is about 5 watts per square meter, which is a lot, actually, at this time. So you can really influence climate as you move up to these longer scale sunspot cycles. Now that's very interesting, so that provides a great explanation for you can have some actual major heating and stuff across the world. But in my part of the world, or the record that I'm seeing, I think there's another influence as well that I think is more important for what I'm seeing. And this is and this has been some of the arguments going back and forth. I think both things are happening here. There's an influence of UV as well here. In fact, there's a, oops, I can get back up, I pushed the wrong button here, that one right here. Yeah, right there. There's about a 0.4% increase in solar shortwave UV radiation under solar maximum conditions around here. And that has an influence down at low latitudes. It'll affect the ozone concentration, it'll have an impact on radiative heating, but I think of most importance to me, it has an impact upon zonal circulation. And if you can turn your mind back to the beginning of the talk here, I was talking about Aleutian Low and North Pacific High affecting the Northeast Pacific, but also the jet stream, okay? So we're going to come back to that right now. So what you end up with, there's sort of an increased penetration from the stratosphere down to the troposphere of these planetary waves, i.e. the jet stream, moving down here, and that changes the way they move a little bit. And again, I told you we always watch this rope. That's what the jet stream is. It's a big rope, and it's being whipped around the world all the time. It goes north, and as I sit in Ottawa, I can hardly wait for it to be pushing further north, and we get warmer days even in the middle of winter, or in the south you'll get some very terrible polar blast. So this is varying backwards and forwards all the time. And the influence up in my region right here, this is where our coring is going on. Again, the Aleutian Low dominating in the winter, North Pacific High more in the summertime, is it's a straight connection. This jet stream moves the Aleutian Low and the North Pacific High around in this region. In fact, there was an interesting paper by Hamid and Lee in 2003, which actually documented the formation of the Aleutian Low and North Pacific High. Their center of action, and that's a fancy word for where they form every year because they're seasonal, moves north and south and east and west along with the sunspot cycle. Okay, so they will move this way and that way as they want. The Aleutian Low goes 500 kilometers east-west and 700 kilometers north-south, and that's going to have an impact upon the nature of the upwelling that's going to go on in the particular region that we're working in. And so so here it is right here. So remember I told you that North Pacific High is great because that results in these clockwise flow of winds, and you end up with lots of upwelling. Well, as you have these Aleutian Low and North Pacific High moving around a little bit, being kicked by the jet stream periodically here, they're going to eventually move around so that places like my Effingham Inlet are more in the sweet zone, okay, for the winds that are going on. So the driver then of this particular model is that you have the sunspot cycle, the celestial modulation that's going on around here. That has an impact on things like cloud formation, but most important for me in this region is the impact upon circulation anomalies, i.e. the jet stream influencing Aleutian Low, North Pacific High, so it's moving these things around. These are moving up to 700 kilometers in North Pacific High and Aleutian Low. And that has an impact. It's either going to result in enhancement of the upwelling going on, or it's going to make it worse. And this is what we're seeing. Okay, and it's a pretty direct connection. And there's people often talk about legs in the system, but this one's pretty direct. In this one, moving through 1 year, I think I'm seeing a pretty much close to a 1-to-1 correlation. Now I'm going to show you a little close-up actually about how dramatic these shifts can be, okay? This is these Gleisberg cycles coming in and coming out on this is the wavelet right here, okay? So we're going to look at this guy right here. So in our records we see evidence of periods of low sun activity and high sun activity going on at different times in here, and you can recognize low sun because if you actually lay the core out beside these wavelets, you can see that their thick clay laminations are linked to wet conditions, or if you have some thin laminations are linked to dry conditions in here. So we can actually see them. So I'm going to show you a record which spans this spot exactly on this particular record. And here it is. Okay, so here's the spot right here. Here we are looking at these layers in here. And all I want to draw your attention to in this particular diagram, these are North Pacific High dominated high sun. And when we have that dominating, we have lots of upwelling going on. The phytoplankton love it. They're getting lots of nutrients and so on up the food chain. The fish love it. Everybody's loving it for long periods of time, for centuries, in fact, around here. Then all of a sudden, it's like that, okay? There's a shift. And this shift, imagine if you're an Indian living in that area around here and you're going through great years of fishing and all kinds of stuff going on. All of a sudden, this time right here, we switched over to another regime, and the regime switched now to one dominated by the Aleutian Low in this region. It's not like it's all year long, okay? This is just, you basically just change the impact for a little longer in the season, and it's enough to impact the phytoplankton and so on enough that the fish don't like it anymore and they move on someplace else. And so again, here's the Aleutian Low North Pacific, or the influence Aleutian Low North Pacific High. So now we're looking at an interval here where it's dominated by lots of rain, and we're seeing lots of these winter sort of laminations going on here. So this changes that can occur are almost instantaneous across the season as we move from one regime to another regime. And this is analogous in many ways, I think, of looking at, say, Gleisberg cycles that we even have seen through the Little Ice Age and so on. So here's one, the Maunder minimum. Here's the Dalton minimum right here. Here's another Gleisberg cycle later on. And we can see these sort of, I think, the same sorts of analogies. So my Gleisberg cycles I see fading in and fading out in the Northeast Pacific 4,400 years ago and all through that entire record, I think are analogous to things that we see now, and people are making projections as to what might go on in the future. Now, I'm just going to move north for a minute right now and show you the same sort of relationship, but different, okay? So this is down, I just showed you this upwelling region down in here, so all the upwelling, and this is what the story was here. Now we're moving across this transition now, the transitional domain, into this inlet complex right here. And I showed you a picture out a few minutes ago. Basically, it's buried in behind islands, and there's some other issues around here. Mainly, here's this inlet complex. It's separated from the open ocean around here, and even there's islands out here too, by this place called Netwatco Rapids. And if anybody sails or anything, this is interesting because the flow here is something like 8 meters per second. Okay, this is one of the fastest, highest tidal flows you're going to find anywhere in the room, or anywhere in the world. Have a look also, these little signs in here. At slack tides, the only time you can get through here, and sailors, if they come through, it's so major to make it in through this thing, they all hop off and post signs on these islands around here that say, I made it or something, or Joe was here or something through here. But here's basically water property data from around here. This is Belize Inlet right here. And what we see with temperature, this shows us, here's some temperatures, little colder temperatures in here, the purple around in here, that are sort of creeping in from the open ocean. Here's oxygen, which shows it's a little bit lower here, and here it is creeping in across this sill, the Netwatco Rapids, just a little bit in here. And here's salinity. And the big thing I want to draw your attention to right here, look at this wedge right here. See, it's green colored, and this is red as higher salinities. There's a low salinity wedge on the top of this. We call this estuarine circulation. Basically, this is a place where there's flow coming out. There's a long inlet right here. There's streams and so on in here, and basically there's a low salinity wedge sitting on top. Now, up in this little sub-inlet off the side of this right here called Allison Sound, here's another one right here. Look at the temperature, and we can see here's some cooler temperatures rates creeping into this little bit warmer part of the inlet. Here's oxygen creeping in right here. Here's low oxygen levels right here, also down to anoxia in here. And again, we see this low salinity wedge right here, which is, again, estuarine circulation flowing out over the top. But the interesting thing is, this is nothing, okay, like what was down in Effingham Inlet. Okay, completely different sort of circulation. There's no upwelling going on, anything. But look what we see in here. We do a wavelet analysis in here. This is biogenic silica, which is phytoplankton, basically what we're looking at in here. We still get Gleisberg cycles popping in, popping out all the time. Also, same thing showing up with grain size analysis in this particular record around here. And again, it's influenced by the Aleutian Low and North Pacific High, but in a different way. Okay, what's the Aleutian Low do in the Northeast Pacific? See, who didn't fall asleep through the lecture? What's the Aleutian Low do in the wintertime? I'm teaching right now. I'm missing my class today. Okay, what's it do in the wintertime? Why is it crappy to live in the North Pacific Northwest in the winter? It rains. Okay, so lots and lots of rain. Summertime, North Pacific High dominating. Okay, so this is the story. Remember, I told you about this estuarine circulation going on top of the flow here. And here, well, before we get to that part, whoops, I'll show you another record right here. This is from a freeze core taken just inside the inlet right here in Belize Inlet. And if you go back, this is a record back from about 1200 AD up to the present time. These are called foraminifera here. These are protists, which are basically, these are benthic organisms that have little amoebas with shells on them, basically, which are good oceanographic indicators. This is interesting. As we move down this record and we do something called a transfer function in this region, basically what you do is you take all kinds of surface data, figure out what the temperature is and salinity that are correlated with certain faunas, and then you can translate it down core. So basically what it tells us is that early on, prior to about 1500 in this area around here, it was anoxic down the bottom, and then the oxygen levels came up and the temperature dropped off. And so we could actually ascribe a value to that doing a transfer function. And so what our model is for up in this particular region, how it differs from the south, but again, the Aleutian Low and North Pacific High is dominating this place in here. During this early phase when there's no oxygen around here, this is a time when the Aleutian Low is enhanced. Remember, somebody just said the Aleutian Low makes it rain, okay? So in these narrow inlets around here, where it's very difficult on the turn of a tide to get even the water to turn around this place because it's so narrow at that Netwatco Rapids around here. So basically the sea level never, ever gets even out basically as you move across the tide turn here. You end up, when there's lots of rain, you have lots and lots of estuarine circulation going around here. That blocks ocean flow getting back into Belize Inlet around here, and the bottom becomes stagnant, okay? No oxygen around here. Then as we move on in time here, things begin to change. As we move into the Ice Age around here, we ended up with the North Pacific High began to dominate in this particular region around here, and we had less flow coming out, but that allowed us to get a little bit of the open ocean water to get in through the Netwatco Rapids around here, got some oxygen in here, and it actually began to become more oxygenated, and that's the signal that we see, okay? Again, it's the North Pacific High and the Aleutian Low, but we're not seeing upwelling anymore. We're seeing changes in the circulation, but it's interesting that we have two completely different places here with a very, very similar sort of record. So, anyway, that's all I want to say, okay? This is not as general a talk as many around here, but I found it quite exciting, okay? The results that we had around here, that in this Northeast Pacific region around here, and this could be applied to all kinds of studies I've seen in various places around here, that this sort of, the natural celestial phenomena that we see around here is a really principal driver of climate in this region, but also very important, that has a very profound influence upon biological systems, like the fisheries, and this is basically what we have to report in there, and that we can have very significant climate variation and productivity variation on all kinds of scales, and at least through the 5,000-year record we have, it's very good. And this is, I've just showed you a couple of cores. We have a large number of cores that show the same sorts of patterns in here across a very broad region. So I'm very confident that the signal we see is good, and I'm ever so happy that people like Svensmark and so on have presented their models, because I now have a way to explain this that was not possible 5 or 10 years ago. So thank you very much for your attention.